Hello, my name is Sam, and you're watching another episode of ExpressiveSyntax. This is the show where together we learn about programming. Today, I've got a very special treat for you. In celebration of Pi Day, I'm going to do this, show you this talk that I did at a local meetup and at work. It's fun, it's silly, and I hope you enjoy it. So, this talk is called Pi for Programmers. It's about pie. I thought it'd be fun for Pi Day to, rather than eat a bunch of pie, well, no, in addition to eating a bunch of pie, to also calculate the value of pi using various nerdy, mathy, programmery methods. So, yeah. So we'll start with some really old methods that the ancient Greeks were using to figure out the area of circles and things. We'll talk about some advances with infinite series, and then end with some super fast, super efficient methods of calculating pi. And we're going to do a couple different things. We're going to use a game engine to visualize some stuff. We'll do some stuff right in the command line, right in the REPL. Yeah, it'll be fun. I hope we learn some stuff about pi or about programming. So I'm going to start by asking, how many of digits of pi do you know? Post in the comments. So let's see, how many do I know? I think I know about 6. 3.14159. I think it's 269. Maybe I know 9 digits. I'm not sure about that. Anyway, yeah. Post in the comments how many digits of pi do you know. The first 3 should be easy. Here's a hint. Today is Pi Day. 3.14. Yeah, here we go. Pi Day. Happy Pi Day. The first method that we're going to use for approximating the value of pi is what I call the random dartboard method. And the way this works is you take a circle inscribed in a square such that the lines of the square are exactly tangential to the sides of the circle. Or to say that another way, the diameter of the circle is exactly equal to the lengths of the sides of the square. And then we throw a bunch of darts at this target so that they land randomly. I have some friends who are really good at darts, and they would always land in the circle, but mine would be pretty much random. We're going to use a computer to make it really random. Okay, so how does that help us? Okay, so the number of darts that land in the circle divided by the number of darts that land in the square should be about proportional to the area of the circle divided by the area of the square. And that should sort of be intuitive. The number, right, because if they're really random, the ratio should be about the difference in the sizes between those two shapes. So, how does this help us get pi? Right, the area of the circle, well, what's the area of the circle? The area of the circle is pi r squared. There's pi in there, so we can use that to get the value of pi. Area of the square is the length of the side squared, or in this case, 2r squared. This. So then we have pi r squared over 2r squared. The r squares cancel out. So we don't, because you think about it, it makes sense. This works for any size square and circle. So the r's cancel out, and we're left with pi over 4. Is the proportion of darts in the circle divided by darts in the square. So then all we need to do is just throw a bunch of darts, count up how many are in the circle, how many are in the square, multiply by 4, and we get pi. Yeah, so let's do that. The way we're doing this is with Ruby. Ruby's my favorite programming language. So we're going to use Ruby. We're going to use this game engine called Gosu to help us visualize the dartboard and the darts. It'll be really neat, I think. So I've already got kind of an outline here, and I'll walk us through it. So we require Gosu. This is our game engine. This is like pulling in the Gosu library. We make a class called Dartboard that inherits from Gosu window. So this is where everything shows up on the screen in our window. We have a diameter. The radius is half the diameter, of course. We initialize our dartboard using the diameter as the width and height of the window. So super calls initialize on the window, and we pass in diameter for both of those values. And then we make I want to be able to see a circle on the screen. So I'm using this circle, making this circle variable, and that's a Gosu image. And we're just passing the path to a circle a picture of a circle, basically. Nothing in the update because the circle doesn't move or change at all, so we don't need to do anything in update yet. And in draw, we draw the circle. So, one important detail here, we draw it at 0, 0, 0, the origin, but in Gosu, the origin is the top left, and not the middle like it is in math class. Like if you're thinking back to math class and picturing origin in the middle, move that up to the upper left. So origin is like here. Or gosh, I don't know if this software flips the image that's getting shown here, but yeah, top left. Anyway, so X, Y, and Z, right? 0, 0, 0. And then we make a new dartboard and call the show method on it, and that's what shows it on the screen. So I'm going to run this code so you can see what it looks like at this point. Ruby dartboard. And yeah, just a circle on a black background. Nothing too fancy at this point. But we can start adding to this. So I want to start by making a Dart class. And this is going to have, this is going to have those same three methods in initialize, a update, and a draw method. And it's going to have a couple attributes. Adder reader. Yeah, there we go. X and Y. So this is the location, right? Where it is on the screen. And we want X and Y to start out in a random spot, right? Both of those we want to be random within that square. So X equals, we'll use the random function to get a random number between 0 and 1, and then multiply that by dartboard diameter to get somewhere an X that's within the width of the dartboard. Similarly, for the Y, we'll use the random function to get a random number between 0 and 1, multiplied by dartboard diameter to get a Y value that's within the height of the dartboard. What else do we need? I think that's good for now. Let's think about what we need to draw this. We're going to use Gosu. There's a draw rectangle method called draw rect. And this takes, I think, 5 parameters. It takes an X and a Y, so that's easy. It takes a width and a height. So let's just do 3 and 3, because we want it to be a little dot on the screen. And it takes a color. So actually I'll make an instance variable for this, color, and initialize that in the initializer. So color is equal to Gosu color. What color should we use? If you have a suggestion, leave it in the chat. Let's see. For now, I'll go with red, I guess, unless somebody wants to suggest something else. I'm open to suggestions. Cool. Oh, you know what? Let's make an instance variable for the size, too. At size equals 3. Because I don't like using magic numbers like this. It's much more descriptive to say this is size, and this is size. We don't need... Do we even need an update method? You know what? I don't think we do. We will want a method that's called... Because, right, so the reason we don't want an update method is because once we throw the dart, once we make a dart, it shouldn't move or change. It should stay where it is. So we don't need update, actually. But we do want to know whether it's inside the circle or not. So inside the circle, question mark. This will return a Boolean value, so we put a question mark at the end. We'll come back to this in a sec. For now, let's just get our darts drawing on the screen and see that they're actually working. So I'll do dart equals empty array. This is actually darts. So this is the array that holds all of our darts. A list of the darts that we have. So now in our update method, we're gonna use the shovel operator to add two darts, a new dart. Dart.new, and this calls the initialize, sets up all this stuff, and then we just need to draw it. So we want to draw all the darts, so we can use map to call the draw method on each of them. Map draw. So this goes through all the darts and calls this method on each of them. So now we should see some darts appearing if we did this correctly. Let's see. Dartboard? Yeah, nice. That looks great. You know what? They're a little bit faint there inside the circle. I wonder if maybe I'll draw them after the circle so that they're, or I could make this -1. Does that change how this appears? What I'm trying to do is make them less faint. Yeah, there we go. That's better. So now this circle that we have is semi-transparent, so we could see them through the circle. But this lets us see them much more clearly, which I like. This is a bit slow. So we can each update add a bunch of darts. Let's do that. Let's do like 50 dot times and then do this. So each update will add 50 darts rather than just one dart. Throwing a whole lot of darts. And the reason I want to be throwing a whole lot of darts is because our estimate of pi will be more accurate the more darts we throw. So I want to throw just a whole bunch, and we'll get a better value for pi. Or more accurate value for pi, I think. So I'm going to stop this and just see how that looks. Yeah, that's way better. Filling it up much faster. Cool, okay. So now we get to some interesting stuff. Now we want to know whether the dart is inside the circle or not. So to do that, we need to do some math. I'm going to go back to my slides. So what do we know at this point? We know the location of our dart, the x and y value of it, right? And we know the middle of the circle is at RR, right? Because remember, the top left is 0, 0. So if we want to get to the middle here, that's RR. I sound like a pirate. R. I make myself laugh. Anyway, so we have the x and the y, and we have R and R. And we can get the length of these two sides by subtracting R from x and R from y. And what we want to find out is the length of this hypotenuse. So, does anyone can you think of a theorem or a formula that will help us with this triangle-looking thing to find the length of a hypotenuse? Yeah, you guessed it. Pythagoras in the house. We're going to use the Pythagorean theorem to get the length of this side. And so we just need to substitute for a and b. So a is x minus r, and b is y minus r. And for c, what we want to know is this hypotenuse less than or equal to the radius of the circle? Because then, if it is, it's inside the circle. So this is going to be our formula. X minus r squared plus y minus r squared less than or equal to r squared. And if that returns true, then we're inside the circle. So I'm gonna plug that in. So we have r is equal to dartboard radius, and then at x minus r, and we square that and add it to y minus r. And so it doesn't matter. So you might be thinking, like, what happens if we have a point over here and one of these values is negative when we subtract? And it doesn't matter because we're squaring them, right? Because a negative value squared is the same as the positive value, the absolute value squared. And so, yeah, we don't care. Less than or equal to r squared. So the Ruby syntax for squaring something is this double star symbol. Or raising something to the power, I should say. Star 2 is squaring. Star 3 would be cubing, etc. And actually, let's change the color based on whether we're inside the circle or not. That would be fun. So let's see. How would we do this? Inside the circle. And we'll just use the ternary operator. So if this is true, we want the color to be. Ooh, if you have suggestions, leave them in the chat window. Otherwise, I'm gonna go with red again. Gosu. Oh my goodness, I can't type. Color red. So that's if it's inside the circle. If it's outside the circle, let's do green. I haven't gotten any suggestions yet. I'm going with green. Gosu. Color green. So now we should, if we're right, we should see different colored darts show up in different places, right? Yeah, we got green on the outside, red on the inside. That's beautiful. Okay. So now all we need to do to get the value of pi is find the darts. Remember, find the darts inside the circle, divide by the darts inside the square, which is the total number of darts, since all of our darts are going to be inside the square. We multiply that by 4. We should get pi. Let's try it out. So in our update, we'll do this each update. Pi is equal to. So how do we find the darts inside the circle? We'll use, let's see, what are we going to use? Darts.count. To get the number of darts inside the circle, we'll call the inside the circle method. So the way the count method works is it returns the number. Well, I'll just write it out first, and then it returns the number, the integer. So it counts up the number of times this returns true, basically. So if there's 50 darts inside the circle, it returns 50. Okay, so that's not pi yet. We need to divide that by the total number of darts, which is darts dot length. The length of the array should be the total number of darts. And we multiply this by 4. Ooh, here's an interesting thing. Why do I need... So this actually needs to be 4.0. Do you know why? Why you can't just put in 4 here? Leave your comments in the comments section. It's pi. So now we're just going to put pi to the console, print it out. And hopefully, if we've done things right... Oh no, we haven't done things right. I just can't spell, that's why. Length. Yes! Yes! Look at that! That is fantastic. Oh man. Nothing more beautiful than a good simulation. What an excellent dartboard simulation we have. And look, we're getting close to pi. 3.142? Pretty good. Oh, we're getting further away now. Alright, I'm going to let this go for a couple more seconds and then stop it and see what the value of pi is. Dun, dun, dun. Hut. Okay, so the value of pi is 3.14609. I guess I was wrong about it being other than this. 3.14609 is the value of pi, apparently. But actually, so I'm clearly it's not. There are other ways to calculate the value of pi. We could also use some infinite series to calculate pi. So before I get to the infinite series we use to calculate pi, I'm going to do a little bit warm up here. So this infinite series, 1 plus a half plus a fourth plus an eighth plus a 16th is equal to 2. And it should kind of be intuitive. Zeno is famous for, Zeno's paradox. If you go, you'll never reach the finish line because you have to go halfway and then go halfway again and then go halfway again. So then, how do you ever cross it if you keep having to go halfway? There's a joke about this. An infinite number of mathematicians walk into a bar. The first one orders 1 beer. The second orders half a beer. The third one orders a quarter of a beer. And the next one's about to order an eighth of a beer when the bartender just shakes his head and pours 2 drinks and says, "You mathematicians need to learn your limits." Yep. Anyway, so there's this infinite series. This one is not as intuitive. What does this add up to? 1 plus 1 squared plus 1 over 2 squared plus 1 over 3 squared, etc., etc., etc. Any guesses? So, here's a hint. It has to do with pi, right? This whole thing is about getting the value of pi. So there's pi in here somewhere. The question is, what does this actually add up to? And this problem was posed in 1644. And mathematicians worked on this for 100 years. Nobody came up with anything. It took a mathematical genius to solve this. This guy finally solved it almost 100 years later, and it was one of the things that helped make him famous. For the longest time, I pronounced his name wrong. I thought it was Euler, and I'm pretty sure I went into interviews and so there was back when I was a baby programmer, there was a website called Project Euler is the actual name. I called it Project Euler, but it has programming problems, math problems, and I was practicing math problems and doing some practice programming and feeling really proud of myself. And I'm pretty sure I bragged about this in interviews, and now in retrospect I realize that I probably pronounced the name wrong, because I only learned recently that this name is actually pronounced Euler and not Euler. Anyway, learned that lesson. So Euler is the guy who solved this, and Euler came up with this answer: pi squared over 6. I wouldn't have guessed. And I know this syntax is kind of intimidating, but this is just the same as this. It's another way of asking the question or stating the problem. So, and I'll walk you through it. So this sideways m thing means the sum. So we're taking the sum of a bunch of things, and this is where we start, n equals 1, and this is how far we go. So the bottom is the starting point, and the top is the end point. So we start with n equals 1 and go to infinity. And then for each term, we add 1 divided by n squared. And yeah, another way to say that is the sum of the reciprocals of the positive square integers is equal to pi squared divided by 6. So all we need to do to get the value of pi is add an infinite number of these. No problem, right? Actually, computers are quite bad at infinites, but computers are quite good at large numbers, very large numbers. So we can add lots and lots of these and get maybe a better estimate of pi than we did before. And this is actually pretty straightforward. I'll show you. So we're going to start with 1, go to 1,000,000. Is that a sufficiently large number, sufficiently close to infinity? And we'll do for n in that series. We want to add to our sum. So I need a sum variable, right? Sum equals, starts at 0, and we plus equals to add to it. And we want to take n squared and divide by 1. But again, this needs to be 1.0. And like before, the reason this needs to be 1.0 and not just 1 is because we're dealing with small numbers less than 1, for these fractions. So if we did 1 divided by n squared, we get 0 if we were dealing with integers. But we want the floating point version, so we're going to make 1 a floating point rather than a integer. Okay, so this gives us the sum. This gives us this part of the equation, right? What we need to do now is multiply by 6 and take the square root in order to get the value of pi. Sort of cancel out this side. So pi is going to be equal to sum times 6, and there's a handy math function in the math library called square root. I think you can just do math dot square root like that, and we can get pi, and and then I'll print pi. Oh, fingers crossed. I hope I didn't make any mistakes. Ruby Euler. Euler.rb. There we go. 3.14159.169. Yeah, I think that's pretty good. I think that's accurate to here. I think this is supposed to be a 2. But, you know, if we round up, that's pretty close. And so with 6 digits of pi, that's a huge amount of accuracy. You could calculate the circumference of the Earth to within a meter with 6 digits of pi. So, yeah, not bad, not bad. I'm gonna do a couple more pi things. So, okay, I'm gonna go back. I should move this slide. So we started off here, and now we're in the 1700s. This spike here is pretty much completely because of Euler and the discoveries that he made, and the mathematicians that were working with him. And notice this is a logarithmic scale on the left. So this is okay. So I'm gonna walk you through this chart. This is the record for approximations of pi in number of digits. Years on the bottom, number of digits on the left, and it goes up extremely slowly. Even a mathematical genius, like, he makes a blip here, but it takes until we get to the 1950s to make some real progress. And the reason that this happens, this spike happens all of a sudden, is because this is when we started getting mainframe computers and really fast, computing power, and it's only gotten better. And so the next method that we're going to look at for calculating pi is this one. From the Chodnovsky brothers. So these are the world record holders for number of digits of pi calculated. They've broken the record multiple times, and I think now it stands at something like 22.4 trillion digits of pi calculated, which is just mind-blowing. And the formula that they used is something like this. It's another infinite series, right? It's got that sideways M symbol for the sum of all the things from 0 to infinity. But this converges on pi much more quickly. If we just do the first term of this series, we get 12 digits of pi, which is it's incredible. And actually, doing the first term is actually pretty easy, because we start at 0, so 0 to the k power is 1, and we cannot worry about it. 0 times 6 factorial is just 1, so we cannot worry about it. 0 times this just becomes 0 when we add it to this. So we don't have to worry about any of this stuff on the top. And again, like this, we don't have to worry about. This we don't have to worry about because, again, k is 0. It makes our lives easy. So the only numbers here that we have to worry about are this one, this one, this one, and the 12. So we can get a really good, we should be able to get a good estimate of pi with just a couple numbers. And I'm going to do this in one line. So I'm just going to use IRB. Let's see if I can get both of these on the screen at the same time, because that would be helpful. Yeah, there we go. Okay, so I'm in IRB. I'm going to do 13591,409. That's this number divided by 640,320. This raised to the power of 3.0. Oops. What happened? Something weird just happened. 3.0 divided by 2.0? Okay, phew. I don't know. Yeah. Okay. So we're working on it. Okay. So that's the first term. Now to get the value of pi, we take take this, multiply by 12, right? Because we multiply by 12, and then finally, so over on the left side, it's 1 over pi. So to get the value of pi, we do 1 divided by this, and we should get, yeah, that looks like pi to me, 3.14159.2653589. I don't remember. I think that's pretty good. Let's compare it to, so that's pretty amazing. The best though, the most efficient, easiest way to calculate pi, and this is only because we're working in Ruby. Ruby is super powerful and it gives you the best tools. So here's the best way to get pi. We just do math ::pi, and there we go. We get 15 decimal places of pi, which is enough to, with this many decimal places, this much precision, we could calculate the circumference of the solar system to within a centimeter. If I've done my calculations, back of the napkin calculations right, this gives us a huge amount of accuracy. How close is the Chavnovsky one? So this 9.2, 265, 35897, 3. Oh, so it just goes wrong at the end there with the last couple. This gives us what, 12 digits of pi? 9, 7. Anyway, that has been my Pi talk. I hope you learned something about programming or something about math, something interesting. I hope you celebrate Pi Day by doing some mathy Pi-related calculations of your own. Oh, I should show you, if you're interested to get the slides for this, it's slides.com/sambackus/Pi-Day, Pi-Day. You get the slides there. If you want to get the code that I used, this is all on GitHub, github.com/sbackus/calculatingpi. I think this is a public repo, so yeah, go ahead and grab that, play around with Pi a little bit. Have fun. Thanks for watching. Happy Pi Day. I will see you all next Thursday. I stream every Thursday at 7:30. We're going to be back to Ruby cones, I think, and trying to wrap those up. So tune in then. If you want to see me, if you missed the stream, you can also, I post these to YouTube. Those are at YouTube ExpressiveSyntax. I'm not sure what the URL is, but you can search for them. Anyway, thanks for watching. My name is Sam. This is ExpressiveSyntax. Catch you next time. Bye.